Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of Module 6, which is on electron beam based powder bed additive manufacturing. So, in this lecture today, we shall discuss about the following topics. First, we will discuss about the powder beam based powder bed additive manufacturing system, its working principle and subsystems. Then we shall discuss about the process cycle, the powder which is used for EB based powder bed additive manufacturing, and what is the scanning system which can move the laser beam onto the powder bed. Then we shall discuss about some challenges associated with the process, and in the end we shall discuss about the physics behind the beam powder interaction. So, if you recall this classification for powder additive manufacturing, where it is divided into two categories, one based on powder bed processes and another powder feed based processes. We already discussed about powder feed based processes, and in the powder bed it can be further divided into binder based processes or energy beam based processes. The energy beam based processes could be of two types, either of laser beam based powder bed AM technologies or the electron beam based powder bed AM technologies. We have already discussed about the laser beam based powder bed technologies. In that we discussed about SLS and SLM, and now today our focus will be on the electron beam based powder bed additive manufacturing. So, this is how typically a powder bed system will look like. It used to have a powder delivery system like here on the left side. However, the popular machine available in the electron beam based powder bed additive manufacturing system, the top powder delivery system is utilized. This is mainly because the chamber size should not increase beyond a certain limit, because if you increase the chamber size, it will take a lot of time to create the vacuum inside the chamber. Therefore, in this process we try to minimize the volume of the chamber so that the vacuum can be achieved quickly and your process or the production time can be reduced. However, to keep our discussion in a similar line, I have made a bottom powder delivery system which is shown here, but like I said, in typical EB based systems, top feeding system is used. So, this reservoir provides the right amount of powder to a powder recoating system. Here it is a blade, and typically in electron beam based powder additive manufacturing system, a recoater blade is used to recoat the new layer or to deposit the new layer onto the powder bed. Then this right side chamber is corresponding to the build plate, where this is the build plate and it is going downward each time by the required layer thickness. As it goes down, it creates a cavity here and a new layer of powder is spreaded onto this cavity by the recoater or the powder recoating system. Once the new layer of powder is available, then an electron beam falls onto this top layer and deflect in the XY plane as per the requirement to melt the powder particles in the selective region. Here, of course, the joining mechanism is governed by melting instead of sintering, like in the case of laser for some cases. The powder material usually used a metal, because there should be a proper conductivity between the powder particles and the substrate so that the electrons can complete the cycle those are falling onto the powder bed. Therefore, usually this process is applicable for metals. The scanning system utilizes some magnetic coils here that I will explain in detail, and that makes the electron beam to deflect in the XY plane appropriately. Like I said, powder delivery system popularly used in EB based powder bed additive manufacturing system is top feeding. We have already seen what is top feeding in our last lecture. So I am not going to describe it again. So this top feeding used to be here like in the form of hoppers, and that provides the right amount of powder to the powder recoating system. The recoating system is nothing but blade. Here other options are not much explored like roller, slotted feeder or the electrostatic method of spreading the powder. Conventional blade is popularly used. Then the build environment. The build environment in the case of EB based powder bed additive manufacturing is used to be the vacuum. It is important for traveling the electrons also into the chamber, because if there be air molecules, these electrons may strike with them and scatter here and there. Therefore, it is very essential to create a vacuum into the chamber. Also, we have discussed when we were discussing about the electron beam based wire additive manufacturing that the vacuum is not only required in the chamber, it is required in the electron gun also to protect the hot cathode to get oxidized and reduce its life. So, a high vacuum is usually created into the welding gun where the electrons or electron beam is generated, and then of course it comes out and strikes to the powder bed, and that secondary chamber as well requires vacuum chamber. But of course, the vacuum in the build chamber is not as high as it is required in the electron beam gun. Next, the build platform. It is like already discussed for laser. It is similar here also. The material which we use for the build platform should be compatible after depositing the layers onto the build platform. It should not create any hard interface so that the cracking occurs during the process itself. Also, sometimes the preheating mechanisms are provided to the build platform in order to maintain the temperature of the substrate at a particular temperature. So, this is a typical cycle for electron beam based powder bed additive manufacturing. So, electron beam based powder additive manufacturing is popularly called as EBM, electron beam melting, and it is the commercially available system by RCAM. So, here you can see there is a electron beam gun and there are two powder hoppers here. These powder hoppers used to deliver the powder to the recoating system, and these are nothing but powder delivery system. And of course, it is nothing but the top feeding. Then when the right amount of powder is available, the recoater used to spread this right amount of powder onto the bed. So that step is called as spreading of powder of layer. That is the first step. So here you can see this recoater is moving and the right amount of powder is available in front of it so that it can deposit the material onto the bed. Remaining material, however, this is actually just sufficient material to get spread onto the powder bed, but if it is remaining, then the remaining material will reach at this location. And then again, when the recoater will move from this end to this end, it can again spread the layer or deposit the layer onto the powder bed. So the next step is the preheating. We have a very important advantage with electron beam that we can move it with a very high velocity. As a result, there is no separate mechanism required to preheat the powder bed or the entire chamber itself. Instead, the electron beam gun itself is used for that purpose. So to increase the temperature of the powder bed, so what they do, they increase the speed of the electron beam and move it with a very high velocity onto the powder bed in such a way that the powder layer which is just spreaded over got preheated up to a certain amount of temperature. After preheating, then the next step comes, which is the melting of the powder. So there are few advantages associated with preheating, and those we will discuss in the subsequent slides. The next step is the melting. After preheating, now the laser beam, which is now sharp. Here the electron beam is quite defocused, as you can see. This is because we want to scan the entire layer, but with a less power density and with a very high speed as well. While do the melting, the electron beam used to melt the powder particles completely, and it is quite focused as well. The electron beam moves again now in the desirable region with a different power density now and can melt the powder particles. This is the third step. So this process from 1 to 3 repeat itself again and again, and hence you can build the part as per the requirement. Finally, once the entire part is built as you are seeing in this diagram, it can be removed and the loose powder can be removed from here. This table shows the typical process parameter used for electron beam melting. The power used for electron beam based powder additive manufacturing is up to 3 kilowatt. The current typically varies from 1 to 50 milliampere. The scanning speed can go up to 10,000 meter per second. The input power is typically 150 kilowatt. The vacuum pressure required is up to 5 into 10 to the power minus 5 millibar. The typical layer thickness vary from 10 micron to 150 micron. The typical roughness we obtain in the part produced by such machine varies from 20 to 20 micron. And of course, the beam diameter varies usually from 100 micron to 350 micron. Here you can see that the beam diameter is not as low as we can achieve in the case of laser. And this is because after a certain value, the electrons start repelling each other and the diameter of the beam cannot reduce further. So this video will give you an idea how this process works. So for example, someone wants to build this particular part by EBM. The first step is of course to do the slicing. Slicing can be done by utilizing a CAM package which we have already seen in our CAPP. Then it is appropriately transferred to the machine software where there are two hoppers in the machine in which we first provide the powder particles, and these two hoppers used to be available on top of the build platform. The powder particles available here now can be deposited onto the bed, and then the powder get melted wherever the beam falls onto it. Of course, before the melting, a preheating operation occur that you can see here in the red color light. So that is showing the entire bed is getting preheated and then the required region is getting melted. So preheating and melting are the two subsequent operations used to occur for each layer, and the entire part is built like this. After completion, the part can be taken out and it can go for a post processing of removing the powder which is adjacent to the part and got stick to it due to high temperature of the preheating. But of course, by the abrasive jet we can really remove the entire part completely and the final part will be available for us. So now let us discuss about how these powders are manufactured for bed additive manufacturing. The first method is the pulverization. Here in this case the bulk material is crushed and grind mechanically to form fine powders. The powder produced from this process are quite irregular in shape but used to attain very fine size. The next method is the electrolysis method. In this method, two electrodes are placed into the suitable electrolyte and anode is made of the required material. Then very pure powder used to produce by this process and the powder particles got deposited onto the cathode. This method is very slow and of course usually used to get very pure powder particles which is required in some cases like of iron and copper. The another popular method is the gas atomization. In this method, the molten material is converted into droplets which further solidified into the powders. The usual shape which is produced by this process are the regular spherical size. So this is a typical schematic of a gas atomizer. Here you can see the material which we want to convert into powder is available on top side in the molten form, and then a gas is supplied from here and the gas is supplied from the center of this. As a result, if the high pressure gas is coming and the molten material is available, it will disintegrate into tiny powder particles into the chamber. We will collect the powder particles at the bottom of the chamber. Those will be of larger diameter and the fine powder particles will be collected onto this particular chamber which are fluidized by the gas. Another variant of the similar kind of process is the plasma atomizer. Here instead of inert gas, a plasma will be used. So as you can see, there are two plasma torch and there is a wire supplied in between. Now this wire is going to be converted into the powder. This wire first will of course get melted because of the high temperature, and as it is moving further and this entire chamber is subjected to vacuum, then suddenly there will be a pressure drop and the droplets will get disintegrated from the molten material and will get converted into the powder particles. These powder particles are further collected at the bottom side and can be used. The plasma atomizer used to be found very much suitable process for making powder particles for additive manufacturing, because it can really generate these spherical powders. So how does this particle should look like? There is an image showing here, which is the microscopic level image of the powder particles, and you can see here the particles are quite spherical in the size. This spherical size of the powder is important to increase its flowability while spreading by using a recoater. The spherical nature of the powder only will also ensure a uniform layer thickness throughout the bed. Also, not always a certain size of the powder particles are used, but a combination is usually used in the powder bed additive manufacturing process. Like a range of powder particles, some particles of larger diameter as well as some particles of smaller diameter are used, and this particular case is an example for a particular case. So here you can see the powder particles of a small size are also available, while the powder particles of larger size are also available. And of course, the average size of the powder particle, which is around 60 to 80, are highest in number. The importance of having this small size particle and this large size particle in combination is to increase the pack density. If the pack density of the deposited or the recoated layer into the powder bed will increase, it will give us a few benefits, such as the conductivity of the bed can be increased and hence few defects such as smoking can be avoided. Also, if the density is high, the pack density is high, when the electron beam will melt the region, the shrinkage will be less. As a result, you will create or you will melt very similar amount of the layer which is actually you are going to spread. No much shrinkage will be there if the pack density of the powder is good. Now let us discuss about the optics which used to manipulate the electron beam while it's moving onto the XY plane, and this is called as the electron optics. The first important thing is the focusing. We have seen it for the case of wire based EBM. However, we shall just revise this exercise here as well for particularly powder bed additive manufacturing. So in most of the EB gun used in manufacturing, electrostatic field is used for the extraction and acceleration of electron, and the magnetic field is used for focusing, deflecting and correcting the beam. So focusing, deflecting and correction of the beam, a magnetic field is used, and while to give acceleration to the electron beam particles, an electrostatic field is used. So as this is your cathode and there are electrons available here, these are generated by some means, maybe by increasing the temperature of this cathode, and this is achieved by the electrostatic and called as electrostatic focusing. So these powder particles will now attract towards the anode because they are the particles of negative charge, and then these particles are going to attract towards the anode which is positive. As a result, the powder particles will get focused up to a certain point. In this region, the focusing is done by the electrostatic field. Then later on, after this point, the electron will again start going diverge. And now this divergence may not be desirable for us because we want to have a minimal or the desirable spot diameter at the powder bed. So now from this point onwards, the electromagnetic field is used for focusing the electron beam. So a typical focusing coil used in the case of electron beam is shown here. Here, when the magnetic field, appropriate magnetic field is applied, they will apply a force to the electrons, those are moving, and due to this force acting on the electron, they will go closer to each other and the beam will become more dense, means more particles, more electron beams will be available at a particular cross section. As the electron density will keep on increasing, after some time they will get focused at a particular point. Of course, after a focusing point they will again get diverged. So the point from where they are going to be diverged and they attain the maximum diameter is called as the objective distance of the optics, and the point from where the electrons are going to get converged till the focusing point where the diameter is minimum is called as the image distance. Typically, this focal length is given by this formula, which says 1 upon f equals to pi e square by 16 m e naught a b naught square. So here the constants are like acceleration voltage, we are not going to change, the width of the focusing coil will not change, the mass of electron will not change, and the charge on the electrons will not change. Hence the variables are the magnetic field. So here we can see F is inversely proportional to the B naught square. As a result, if I increase the magnetic field, of course we can see that the focusing distance will reduce. And it is obvious, if I increase the magnetic field here, then I will apply more force onto the electrons and they will get converged earlier as compared to getting converged later here. Due to this early convergence of the electrons, the focus distance, which is here to here, now has been reduced if you observe, which was earlier this much. Of course, this magnetic field also depends on the current which we are providing into the coil. Therefore, this relation can be considered now for the focal distance. Instead of considering the magnetic field, we can consider the lens current itself. How much current we are supplying to this, because this current will be also proportional to the magnetic field. Therefore, the focal length can be said that the focal distance is inversely proportional to I square, and that is what you are seeing here. As the current will increase, the focal distance will keep on reducing. So this was all about focusing the electron beam at the particular or the desirable spot. Now let us discuss about how we can deflect, because there is a stationary powder bed. Now the electron beam is coming vertically, but what our aim is to make sure that the spot is not here, it is at a particular location away from the center, and this deflection may happen onto the entire bed. So for that we required a deflection coil. It is very much similar like we discussed for the laser, where we used to have the mirrors for deflecting the laser beam, and that was called as the galvanometer. You have seen the demo also of the same, as well as the working principle, where there is a mirror. When the laser beam strike on it, and as the mirror moves like this, the beam falling onto the bottom can also move here and there. In a similar fashion, here also we want a system which can deflect this electron beam on the XY plane. So for that, the deflection coils are used. Also, when the beam is coming and focusing at a particular point, its shape may get distorted, and there are several reasons for that, such as interference. I'll discuss about it. Also, when you project the beam away at a particular distance, we have also seen in the case of laser beam as well, and that will happen here also, that the beam which is falling at an angle, and if you take a cross section of the beam, at that time the cross section will not be circular, instead it will become elliptical. As the area will increase, definitely the power density will change. In that case, the part you are producing here and part you are producing at another location on the bed may not have the same power density. As a result, then the metallurgical and material property may be different. Also, to correct the shape of the beam, a coil is used, which is typically called as the correction coils. So let us discuss about this deflection coil and the correction coils. So in electron beam gun, the electrons are deflected by electromagnetic lenses. Like in the case of laser, similar way the laser is deflected by mirrors. Here the electrons are deflected by electromagnetic lenses, which generate the force shown in equation 1 here to move the electron beam. This is the typical equation for the Lorentz force, which says that if a particle which is having a charge q moving with a velocity v in a magnetic field B, then a force F will act onto this particle. Now let us extend our analogy for the electrons moving in a particular magnetic field. So consider this is your electron and it is moving in this direction with a velocity v. Assume that the magnetic field is perpendicular to the screen and it is inward. So I am making this sign corresponding to the magnetic field. So magnetic field is inside the screen like this. So when this electron will come into this magnetic field, it will feel a force, and the direction of the force will be defined by the right hand rule. It says if this is the direction of the velocity and this is showing the direction of the magnetic field, then this thumb will show the direction of the force acting onto the particle. So if this is the velocity of the particle, it is going in this direction, and if I move it downward perpendicular to my screen, then this will be the direction of the force acting onto the particle. So as here the velocity is in this direction and B is inward into the screen, then the force acting onto the particle will be in this direction, of course. Let me write it as electromagnetic force. Now as this force is acting and is still moving in a particular direction and particle is having a velocity v, the path of the electron will be circular. So why it will be circular? Let me explain it to you. So assume at an instant here, the direction, the velocity of the particle is like this, right? And the force acting on it will be perpendicular to this v, and it will be perpendicular to the b as well, and b is anyway inside the screen. Hence this will be the direction of the force. Due to this force, the trajectory of the path will, the trajectory of the electron will change, and now assume that it has reached to another position, maybe here. Now this is the new position of the electron. Now this is the direction of the velocity of the particle, and again a force will act onto it, and that will be again perpendicular to this direction. Now again assume if the particle has reached to another position, this will be the direction of the velocity and the force will act perpendicular to it. So it is obvious now from here that the particle is going to move onto a circle, because all the force acting onto the particle are perpendicular to the velocity of the electron, and that is why it is going to move onto a circle, because we know that if it is going to move on a trajectory where the tangent is showing the velocity and the perpendicular is showing the force, then definitely this trajectory will be nothing but the circle. Hence, as now the electron is moving onto a circle, there will be two forces acting onto the electron. Let me consider the particle here, and if this is the velocity of the particle v, of course there will be a perpendicular force F acting onto the same, and that is nothing but your electromagnetic force. Now there will be a force acting onto the particle in the outward direction as it is moving on a circular trajectory, and that will be nothing but mv square upon r. We know that. If I balance these two forces, then only the particle will be in equilibrium. So let us do that. Mv square upon r equals to the electromagnetic force acting inwards towards the center will be equals to QVB, the magnitude of this. Then from here we can find out the value of r, that is the radius of circle onto which your electron is moving. Also, the kinetic energy of the particle, which is half mv square, will be equals to the energy of the particle, which is E into V, where capital V is the acceleration voltage and E is nothing but the charge on the electron. As a result, from here also we can find out the velocity of the particle, which is here. If of course the voltage is increasing, this velocity will also increase. So now we know the velocity, and as a result the other parameters are controllable or known to us. So let us now put this value of V here in this expression, and as a result you will have R equals to 2EV by QVB. Now let us try to find out this value of theta, because the electron is moving assumed to be on a very large radius circle. In that case what will happen? So let me consider this as a straight line, because I am assuming that the electron is moving on a very large circle. The circle is very large. In that case I can consider the position of electron at a particular distance L, and as a result it will get deflected by an amount x. So I can find out the value of tan theta, that is tan theta equals to, here of course, x by L. Also we can notice that this angle theta will be equals to this angle theta, and if I consider now this triangle where this value is known to us, this is r, radius of the trajectory of the circle on which the electron is moving, and this value is a. Hence I can say that here also from this triangle that tan theta will be equals to a divided by r. Now I have tan theta equals to x by L, and also I have tan theta equals to a by r from the approximation where we assume that this is the triangle formed here. I mean assuming that this is also a straight line. Now in that case, if this is a straight line we assume, and we have made this assumption, if we assume that this value of a is very small, not very large, our assumption is valid, and we can say this a by r is equals to x by L. As a result, from here I can find out x in terms of r, and I already have the value of r, so I can put this value of r here, and the value of deflection of the beam will be given like this. So it is x equals to a L Q V B by 2 EV. So of course, if it is given to me that the value of the width of the coil, the distance at which I am measuring, the charge on all the electrons, V is the velocity of the electron, B is the magnetic field which is given and also depends on the current given to the coil, divided by 2 E electron charge into capital V, that is the voltage difference to get the desirable velocity or the acceleration voltage. So if I am so assume now your screen or bed is here, right? This is your bed vertically. So if you want to deflect the beam at a particular distance from the center, you can easily find out its value by utilizing this formula. And this is how the electron beam is deflected onto the XY bed. Of course, this is a deflection in one direction. Now if you want to achieve the deflection in another direction as well, there must be another coil perpendicular to the same. Therefore, the typical deflection coil looks something like this. There are coils corresponding to the X movement of the electron beam, and there are coils corresponding to the Y movement of the electron beam onto the powder bed. Of course, by giving the appropriate current to these deflection coils, one can appropriately give the value of X and Y to the desirable position of the electron beam, and the beam can be deflected to the desirable position. This can be achieved with a very high velocity, because now I can manipulate my current with a very high speed, and as soon as I change the current, immediately my beam will get deflected with the desirable speed. That is the reason why we are able to move the electron beam with such a high speed. Because if you recall our galvanometer, there was some inertia involved. Though these mirrors are also tiny, you can move at least by 10 meters per second. That too is very high speed, but at least some inertia was involved to move these mirrors by some mechanical means. But here that is completely eliminated. There is no mass which is involved which we are going to deflect. Instead, there are electrons, and dynamically we can change the current, and that will apply different force onto the electron, and as a result the electron beam will get deflected with a very high speed, and that may go up to 10,000 meter per second. As we are having very high speed, of course the electron beam need not to move always onto the straight line while scanning any path. Instead, it can move in different path, like this trochoidal path, where it is moving, it is rotating like this and moving forward as well. So this advancing and rotation of the electron beam onto the powder bed together can be achieved here. The other patterns are shown here which can achieve to move the electron beam in the desired path. So this was all about the deflection of the beam onto the bed. Now let us discuss about the correction. So what happened when the electron beam are focused by utilizing the focusing coils here? They used to achieve the minimal diameter at certain depth, or maybe at the powder bed itself. So wherever our electron beam is getting focused, that distance from the focusing coil is called as the focus distance. If the focal point is achieved under the bed, I mean if this is the powder bed's top layer and the focal point is under this, then it is called as under focused, and if it is above this, it is called as over focused. Typically, if the beam is falling perpendicularly and you take a cross section, you will get nothing but the circular cross section. Of course, the size of this circle or the circular cross section may vary. It may be larger at the defocal portion and it will be smaller at the focal portion towards or closer to the focal point. But it may happen that there is not a proper alignment between the cathode and anode itself. As a result, you may have some larger density of electron on one side and lesser density of electron on another side. In that case, your beam which is getting focused at a particular point, and if you take any cross section, that may not have a circular cross section, or beam may get distorted. It is also very much possible sometimes due to the interference, because if the electrons are moving and they are having a charge, right, and they are going to strike to the bed, these moving particles also used to have their own magnetic field, we know that, and this magnetic field may disturb the adjacent particles. Those are moving. So consider that there is an electron moving with the velocity and it is having its own magnetic field. Then the adjacent particle which is moving, and if it is subjected to this or entering into its magnetic field, this particle will get subjected to a force. And as this electron is getting force due to the magnetic field which is of another particle, it will get deflected, and hence your shape of the beam may not remain uniform and it may get distorted. So to overcome with this difficulty, usually stigmators are used. The stigmators are nothing but the electromagnetic coils with multiple poles to use to correct the beam shape. So there is a beam coming at the center, and if there are multiple, and if there is a coil with multi-poles, several poles, and you are giving uniform current to each and every pole, what it will do? It will apply uniform force onto the electron available into the electron beam from all the sides uniformly, and it will tightly pack it so that everywhere it is uniform force and the electron can get aligned itself. And as a result, the shape of the beam can be uniform. This is a typical example of quadrupole stigmator is shown here. As you can see, if this is the particle, it will subjected by the force from all the sides, and as a result, this particle will become aligned appropriately, and as a result, you will get the uniform cross section. Also, the stigmators are not only used to correct the shape just because of the misalignment into the cathode and anode, or because of the interface of the magnetic field, but it may also happen because of the projection of the beam away from the center. We know that if the beam is projected away, if it is not perpendicularly projected onto the bed, instead it is projected like this, as a result you will have an ellipse here while it was a circle here. So we have to correct this shape as well. So now assume that if you have such a coil, what is required, that if you are projecting the beam away like this, you have to provide more force onto these particles, those are along this side, while you need not to give any force to these particles, those are along the minor axis. So the electrons, those are available close to the major axis, will get some force with this multipole stegmiter. As a result, these electrons will come closer and form a uniform cross section. So that is how the beam is corrected whenever you are projecting it anywhere onto the powder bed. Please recall that how we do this beam correction in the case of laser. We do this correction of the beam in the case of laser by utilizing the f theta lens that used to correct its focal length, as well as it used to correct its distortion into the shape. Here the same thing is achieved. Here the same thing is achieved by the multipole stegmators. Now let us discuss about some of the challenges associated with electron beam. The major challenge is again very much similar to the laser based processes, that is the delamination, where the layers are not able to join together, and due to the residual stress and they got delaminated like you are seeing here. The primary reason for residual stress is of course the thermal gradient. If we are able to reduce the thermal gradient, this issue can be eliminated. We have some advantages in electron beam as we are going to utilize it for preheating as well. Therefore, if you are going to do the preheating before actually melting the particles, then the thermal gradient can be drastically reduced in this case. Of course, if there is an inadequate power density, then we may not have a very uniform surface deposited. Instead, it will be uneven or unevenly deposited surface. The another is the powder smoking. The powder smoking is nothing but moving the particle or explosion of the powder particles underneath the electron beam, and it moves here and there. It's the biggest issue actually in the electron beam, and I shall discuss a little bit in detail about this issue, and I'll discuss about its solution also. So here, but you remember that if you are seeing this type of explosion under the electron beam, it is popularly called as the powder smoking. Of course, there are possibilities of getting the porosities, and this is typically due to the trapped gas. Now from where this gas is coming? Because we are using vacuum. But in electron beam, in some machines, helium is usually purged, very low amount, and of course when we purge the helium, vacuum is distorted, but that is happening only into the working chamber, not onto the chamber corresponding to the electron beam gun. Okay, so in that chamber, certain amount of helium is purged to make the powder bed uniform. It's important for other purpose, but if these gases are trapped, they may lead to the porosity. If you are not using any gas, the chances of getting porosity due to gas in the case of electron beam are very low. Of course, the another possibility of having the porosity is because of the insufficient melting of the powder particles. It usually occurs due to the non-spherical particles. Another issue in the powder bed additive manufacturing particularly is volume shrinkage. Here, for example, you are going to deposit a layer. It will have some less material available onto the solidified part. So this is the solidified region and this is the powder region. This is because the volume will get shrink when we will melt the powder particle onto this top layer. As a result, if you see here as well, when the electron beam will write over it, the powder particle will get shrink due to the increase in the density of the solidified particle into the solidified region, and it will leave some cavity behind. So we have to accommodate this, and it highly depends on what is the packing density of your powder. Like I already mentioned, if you are packing your powder particles more compactly, then such cases will get eliminated. But if you are not able to pack the powder particles compactly, then of course such cases will arise, and you have to accommodate it in your CAPP package. You measure how much your solidified region going to get decreased from the powder bed top level and accommodate it in the earlier stage of the CAPP itself. Now let us discuss about the challenge which was corresponding to smoking. It is also popularly called as spreading or pushing of powder, but smoking is the more popular term. So there are two reasons for that. One is the powder particles itself may have some water residue in it or humidity in the powder itself. When the laser beam strike over it, this moisture available with the particle got exploded, and as a result the particle will also move here and there. The another reason could be the momentum of the electrons itself. However, the mass of the electron is very low, we know that, and this region is not very much dominating onto the smoking. The third possible and the most dominant reason for the smoking is the electrostatic charge onto the powder particles. So as you are seeing here, this is a layer of powder particle and electron beam is falling onto it. Now assume that if the electron is striking with these particles, of course there will be three types of electron. Some will transmit, some will backscatter, and some will get absorbed as well. As in the case of the powder bed based processes, the powder particles used to have a very bad contact area, mean very less contact area. As a result, if the contact area is less, we know that the resistance will increase. As a result, the electron will not flow with the same flow as they could flow in a complete wire, right, where there is a uniform bridge everywhere and the uniform cross section. Here the cross section is suddenly reducing, and we know that R is equals to rho L by A, and if area is reduced, then of course this value of R will increase. As a result, the current will not be able to pass from this powder bed. Therefore, these particles will start acting as a capacitor and they will start absorbing the charge from the electrons. As the charge will keep on accumulating on these electrons, assume that I am representing this charge by here Q, and its value is keep on increasing, then what will happen? It will start repelling the adjacent particle. As a result, when the electron beam will strike onto it, these powder particles will just bounce away from each other due to a high amount of charge accumulated on these particles. So this is one major reason for the smoking. Another of the same kind is due to the magnetic field of electron beam itself. So there are electrons moving with a high velocity, right, into the electron beam. They used to have their own magnetic field. As this magnetic field is available here and these powder particles are charged already, right, due to the striking of the electrons and not able to transmit the electrons completely, the particles will get charged, and these charged particles, when they will come under the magnetic field, definitely they are going to be spilled here and there due to the force acting on these particles. So the primary reason for the same are summarized here. One is due to the point-wise connection between the particles. The particles will keep on accumulating the charge and will start repelling each other. And another reason could be due to the oxide layer formation. So if there are oxide layers on top of these particles, that is very much likely because of the high reactivity of the powder particles, such as if I talk about very reactive material like titanium, the oxide layers are quite possible to be having onto the top layer. That also will increase the resistance, and as a result, these particles will act as a capacitor. So what to do? For the first thing we should do, we should try to eliminate this point-wise connection. And second is, we should not have any oxide layer on top. But both of these are very difficult to eliminate. If there are particles and they are spherical in nature, definitely they are going to have the point-wise contact. And if you will not use the spherical particles, then you won't be able to spread it appropriately. So both are contradicting to each other, both the phenomena are desirable. So there can be a compromisation in a different means by utilizing the powder particles of sphere shape but of different size. So if I have a distribution of the particle which I have shown you, like the larger particles as well as the smaller particles so that the pack density can be increased. Of course, there will be still a point contact, but the contact area will increase, and we know that if the contact area will increase, the resistance will decrease. As a result, the electron will be able to transmit appropriately. Also, it is possible by increasing the temperature of the bed, because if you increase the temperature of the bed, the conductivity of the oxides form onto the top layer of the powder will also increase, and as the conductivity of the powder particles will increase, definitely the resistance will decrease, and as a result the charge will not much accumulated, and hence not much charge will get accumulated onto the particles. There is another possibility by appropriately changing the process parameters such as current density and beam size, and another possible method of eliminating this could be the scanning strategy. Like, for example, if you are scanning in this direction, then we should try not to scan the particles available here once again. Instead, we should stop and just come back from here. This is one possible example I am saying. This is because if you keep on moving around this particular point many times, then definitely charge will get accumulated and the particles available there may start repelling each other. So, scanning strategy could be one possible way of eliminating the smoking. So, now let us discuss about the electron beam powder interaction. So, typically when an electron strikes onto the top layer of the powder bed, some amount of the electron will get backscatter. They will strike and backscatter outward. Some electron will get transmit, and the electrons those are transmitting now will move inside. So this is the phenomena assumed to be on first layer, that is of few microns, assumed to be around 15 micron. Then further these transmitted electrons will move to the next region, that is shown here by layer 2. In this region again, some electrons will get transmitted to third region and some electrons will get backscatter. But now the backscatter electrons may not come out of the powder bed, and they will get trapped here inside the powder bed itself. As a result, if they are getting trapped, of course they will get absorbed. Further, after few layers, the transmission of electrons will keep on reducing, and as a result the backscatter electrons will also keeps on reducing, and hence you can see that is why this is the shape of the typical melted zone. Here you can see the top melted zone is not of much width. This is because many electrons got backscattered here. But further, when the transmission electrons are going further, the backscatter electrons are getting absorbed, and that is why in region 2 and 3 the width is quite high. Further, in the fourth region the available electrons are now less, and of course the width of the molten zone will further keeps on reducing in this zone. So this is the typical shape of the molten region when the electron beam strikes at a particular location onto the powder bed. So this is another region. Here you can see corresponding of the zone of the melted powder particles. Here you can see there will be a zone that will be of uniform thickness, but beyond that there will be variation in the width. Variation in the width means there will be less width in the beginning because of the backscatter electrons, and due to the absorption of these backscatter electrons further, the width of the molten zone will increase. This particular diagram shows the number of electrons getting absorbed. They of course are going to follow the rule shown here that says the number of absorbed electron, number of backscatter electron plus number of transmission electron will be constant and assumed to be 1. And if that is the case, assume that in the beginning you are having one amount of the electrons. Now this is the so these are the total electrons available which we are assumed that will get transmitted. In the beginning, of course, the whole amount of the electron will get transmitted, hence the value is 1. But after first layer, as you see in the first layer, the amount of electron those got transmitted have been reduced. So after the first layer, the amount of electrons to be transmitted have been reduced, and they are now assumed to be here, if you consider it, 0.75. Some amount of the particles got absorbed and some amount of particles got backscattered. So this dashed line shows the amount of particles got backscattered, and this scale is reversed here. Okay, this is 0. So in the beginning NT is 1 and the backscatter particles are 0, and of course if this is 1, this is 0. If you use this equation, we will get Na absorbed also 0. But when the first layer completed, there will be a finite value of Nb and there will be a finite value of Nt. So assume that if Nt is like 0.05 and Nt is 0.75, in that case your Na, the absorbed particle, will be nothing but 1 minus 0.75 minus 0.05, and that is shown here in the hatch region. Okay, so this is the amount of particle got absorbed, this is the amount of particle got backscattered, and this is the amount of particle got transmitted. Further into the next layer, if I reach to the end of this layer, I can see that the amount of particles getting transmitted have further reduced and the available particles are less because more amount of particle got absorbed here. Of course, a certain amount of particle got backscattered again and went outside the powder bed. That now remains constant always and doesn't change much because some of amount of the backscatter electron get further absorbed. That is why this curve is not going like this. It is just dropping straight in a straight line because this amount is constant now. But the region for the absorbed electron is getting increased as the depth is increasing, and that is why this shape is observed. This particular curve shows the absorbed energy fraction, and here the energy absorbed by the maximum energy available on the top of the bed is shown here. As we go down with the depth, of course the absorbed energy will keeps on increasing, and hence that is why this curve is moving from 0 to 1 towards 1 like this. So this was all about the electron beam based powder bed additive manufacturing, and now in next lecture we shall discuss about the binder based powder bed additive manufacturing systems. So thank you very much.